That was just a problem with our Zoom session. And hold on, where is my Zoom? Okay. Do we need to readjust the Zoom microphone? Let me see whether that is still, okay, that's still in manual mode. Are you guys able to see me fine? Sorry, see and hear me fine? Okay, very good. So let me proceed with an example on system identification, okay? Oops. That's not the pen that I need. So here's an example on system identification. This will basically show you that system identification is not something that you are entirely new to. In fact, we have done this kind of thing in 302. We just didn't call it system identification. Okay. Let's write the question from first principles. Engineers have come up with a second order linear model for a physical system. Linear model for a physical system. Component specs have led to determination of some parameters but there are still some unknowns. Okay, so we are writing this model GM of S as A over, so A is an unknown, capital A is an unknown, S squared plus small s, small a s plus 18. Okay, so that means A, capital A and A are unknown model parameters. Okay, so that means they cannot be directly measured or obtained from components, from components specs, let's say. Okay, so how can we obtain the complete model is the question. Okay, how to obtain the full model. Okay, and the answer to that is based on our previous knowledge of second order systems. Okay, so what we need to do is to experiment with this system. So we're gonna say we need to perform an or multiple experiments with the system. Let's say we apply a unit step function to the system. Since this is a second order system, we will have our usual response, right? So we will have, let's say this is our unit step. Okay, this is our u of t. And the system's output gonna have a different shape. It's gonna be essentially a function like, okay, so that's gonna settle into a different final value. Let's say this value is 2. And we look at this and we make some measurements. Okay. For second order systems, we have a pretty good understanding of how model parameters are reflected into the actual response. Okay. So this system identification does not need to be iterative or does not need to be, multiple experiments and optimization and stuff like that, because we have a good understanding of how model parameters correspond to the actual response. For example, from the given physical response, right, let's call this yt, I can measure basically the time it takes for it to settle into the 5% band. Okay, so I can measure this, and let's say it turns out to be 2 seconds, right? This is measured from the response. Okay. I can make other measurements. I can make, for example, I can make MP% here. I can measure the rise time over here. But for the time being, I'm saying that I have made just one measurement, which is the settling time, which is equal to 2 seconds. Okay. Now, obviously, given the settling time, and given that I already have partially a system model, I can try to determine model parameters. Can I determine A from this measurement? I actually have another measurement apart from the settling time, which is 2 seconds here. Can you tell me what's going to help me find the parameters? Apart from the settling time, what did I already measure here in this response? Well, yes, that's correct. So steady state error. In fact, the final time, right? The final time of the output. Sorry, the final value of the output, right? The final value of the output, y steady state, is equal to 2. What is that y steady state? It is a limit t goes to infinity y of t. And we know that this final value can also be calculated from the transfer function. That's going to be equal to limit s goes to 0, s times y of s from the final value theorem. And what is that equal for our given transfer function? It is equal to limit s goes to 0, s times the s times u of s times g of s. What was our gm of s? Okay, gm of s. So since we have a unit step function, so that's going to be limit s goes to 0, s times 1 over s coming from the unit step, and gm of s. Oops, sorry. S1 over s, gm of s. Let's calculate that. So YSS, which is equal to 2, has to be equal to limits S goes to 0, S1 over S cancelled. What is GM of S? It is equal to A over S squared plus AS plus 18. Okay? So when I take the limit S goes to 0, these terms cancel out. So that becomes A over 18. And that is equal to 2. Okay? So that gives me one of the system parameters already, which is capital A, which is equal to 36. Okay? From the final value theorem or from the expression of the steady state error, I was able to obtain one of the parameters. Now, what about the second parameter? Okay? Now, we know that for a second order system, the typical transfer function is actually equal to omega n squared over s squared plus 2 psi omega n s plus omega n squared for an underdamped second order system. I know that my system is underdamped because of the response, which already have some oscillations, right? What is the steady state, what's the settling time, TS? It is approximately given for the 5% band from 302. I know that this is over 3 over psi omega n. And that is given to be 2 seconds. Okay? Now, what about omega n? Well, I know, can I find omega n? Sure, because A is equal to omega n squared, and that is equal to 36. Is everything okay with everyone? Bu benim telefonum. Duyuluyor mu şeyden? Titreşimde olmasına rağmen. Masa titreştiği için mikrofona geçiyor galiba, değil mi? So that means I have basically omega n is equal to 6, right? So 2 psi omega n, in fact, I don't even need that because, you know, here I have 2 psi omega n. I don't need to determine omega n. I did, but it wasn't needed because I have A is equal to 2 psi omega n, and therefore 2 and psi omega n is 3 over 2. So that means, what kind of calculation is that? Let me write it down again, okay? A is equal to 2 times psi omega n, and psi omega n is equal to 3 over 2, and that means I have small a determined as well, which completes all of the model parameters. Okay, so my full transfer function becomes simply 36 over s squared plus 3s plus 18. Now, so we performed an experiment, and y of t is the observed response. What kind of a response is this? Well, it's an underdamped response, right? An underdamped response is where you have some oscillations. I mean, if the response was like this, right? it would have been an overdamped response, right? In that case, if that was an overdamped response, that expression that we had would not apply, and we would have a more difficult problem. Okay? Any questions at this point? Çok az geliyor sesiniz. Biraz mikrofona yaklaşırsanız. Yes, go ahead.
Hocam ben bir şey soracaktım. Öncelikle şimdi biz burada iki tane bilinmeyenimiz vardı. O yüzden Y of T'den iki tane şey çektik yani. Step 806 bir de Statement Time'ı çektik. Herhangi iki taneyi alabiliriz değil mi yani?
Okay, so that's a very good question. Let's say that we have measured rise time, we have measured percent overshoot, we have measured the final value, and we have measured the settling time. Okay? From each, in fact, from a combination of these values, you can obtain different versions of capital A and A. Is that correct?
Aynı şeyi bulmamız gerekmez mi? Aynı ağırlığı bulmamız gerekmez mi?
Peki, Türkçe konuşalım. İdealde aynı değeri bulmanız gerekir. Ama bu bir deneysel bir sonuç olduğu için, bir deneysel bir response olduğu için ne bekliyorsunuz? Her seçtiğiniz parametre setinden birbirine yakın ama farklı olabilecek capital A ve A'lar bekliyorsunuz. Doğru mu? Anlaşıldı mı söylemek istediğim? O zaman ne yapabilirsiniz? Yani nasıl bir işlem yapabilirsiniz? Hangisini alacaksınız?
O zaman birden fazla bu işlemi yapıp ortalama bir değer bulmak.
Evet. Yani farklı response üzerinden ölçülen farklı parametrelerden aynı değerleri elde edip ortalamasını alabilirsiniz. Birden fazla deney yapıp birden fazla eğri elde edip onlardan elde ettiğiniz şeylerin ortalamasını alabilirsiniz. Bunların hepsi yapılabilecek şeyler. Başka soru var mı?
Hocam bir tane daha var. Bir soru daha var.
Go ahead.
Hocam bu response underdamp, bunun underdamp olduğu belli oluyor. Ya da bu şey olsaydı critical damp ve overdamp sanırım. O ikisi bayağı benzerdi yani. O ikisi de 2'nin üstüne çıkmayacaklar yani. Onları ayırt etmek aslında zor olmayacak.
Bence kesinlikle daha zor olacak. Şöyle ki en azından burada underdamp'te biz transfer function'ın formunu gayet iyi biliyoruz. Critically damped ve overdamped'de de aslında formun neye benzeyeceğini biliyoruz. Yani bulmaya çalışabiliriz ama belki bundan daha zor olacak. Yani öyle bir örneği deneyebilirsiniz. Mesela overdamped bir transfer function'da bir unknown koyup bulmaya çalışabilirsiniz. Ama buradan daha zor olacak çünkü underdamped response bize bu davranıştaki önemli parametrelerle şey arasında transfer function arasında net bir şekilde daha önceden hesapladığımız ilişkiler veriyor. Okay?
Hocam ben bir şey soracağım. Az önce aşağıda hesapladık da omega n square 18 olmayacak mıydı? Ben yanlış.
Bakalım. Bu arada neden beni sürekli screen share'ime atıyor? Bir saniye. Bakalım. Omega n square A'yı 36 bulduk.
Normalde üst taraf k omega n square, alttaki transfer function'da omega n
Evet.
square oluyor.
Evet.
18
Şurada hatamız var. Şunu düzeltelim. Teşekkür ederim. Okay. So let me close this and move on to a new. Let me see. So let's create a new node. Okay. I don't know why it hasn't. Okay. So
Bu arada yine sanırım yani yanlış yaptık gibi hissettim orada ama tekrar bakabilir miyiz? Kusura bakmayın bu arada.
tabii ki bakabiliriz.
18 olması gerekmiyor. Evet, orası 18 olacak. Yukarısı k omega n square oluyor yani.
Evet, çünkü yukarısı 2 çarpı bir saniye. Çünkü yukarısı 2 çarpı omega n square. Evet, şey hatası yaptık orada arkadaşlar. Bir saniye. Nerede bu?
Aşağısı 18.
Evet, şöyle. Burada a'yı 36 bulduk. Evet, yukarısı 36 arkadaşlar, aşağısı değil mi? Aşağısı 18 olacak.
Evet hocam ve omega n square'ı bulurken 36'ya değil 18'e eşitleyeceğiz.
Evet, aynen öyle. Bir saniye. Bunu ben edit edebiliyor muyum şu anda? Bir saniye. Bu şeyin formatı değişmiş durumda da. Bir saniye arkadaşlar. Şöyle yapacağız. Tamam. Okey. Şu da beni gıcık etmekte şu anda. Şöyle yapalım. Bu 18 olacak. Sonra da ne yaptık? Şurada nerede hata yaptık burada? Şeyde omega n square'ı, evet aynen öyle. Burası 36. Omega n square'imiz bizim şeye eşit olacak. 18'e eşit olacak. Evet. Ama sonucumuzu değiştirmiyor. Çünkü omega n'e ihtiyacımız yoktu. Tamam değil mi?
Hocam bir de Cm'in ilk yazarken bir k olacak değil mi? K çarpı omega n kare. Yoksa a'da 36 değil de 18 gibi olmak.
Bizim standart second order ifademiz buydu. Ama bizimki bunun steady state error'ı 0. Ama bizimkinin 0 değil. Yani bu standart transfer function'ı biz çizerken doğrudan biliyorsunuz input'la aynı değere gidiyordu. Şöyleydi yani. Hatırladınız mı? Bizimki farklı bir değere gittiği için burada farklı bir değerimiz olmuş oluyor. Okay? So I'm closing this. And where is my... Okay. So... All right. So now what I want to talk about is starting actually building models of dynamic systems. Okay. And I want to talk about initially some different types of mathematical models. Okay. And I want to really kind of sketch kind of a space of different systems in the first axis, what I want to put down is static versus dynamic systems. Can somebody tell me what's going to be the difference between these two? Static models versus dynamic models.
Time depends. Parameters change in dynamic.
Not really. That is between time invariant and time varying models. Okay? Static and dynamic is somewhat different. Anyone else?
Is it we model forces more in dynamic models?
Not really. That's not it. Somebody else?
Maybe dynamic systems are like repeated, like sinusoidal or something.
Repeated meaning?
I mean, like sinusoidal, or there will be a loop maybe.
No.
Do we also include transient in the dynamic?
Well, dynamic models have some kind of transients, but you have to be more specific. Anyone else? Who is speaking? Yes.
Maybe in dynamic systems, changing parameters during time or during the process.
If the parameters change with time, that's a time varying system. If the parameters are constant, then it's a time invariant system. Okay? Static and dynamic is actually something else. Almost all systems we have seen, except maybe some components, are actually dynamic systems. The difference between a static system and a dynamic system is that dynamic systems are defined by differential equations. Static systems are defined by algebraic equations. What's happening? Okay. Okay. So okay, my screensaver in my tablet actually closes my screen sharing. So sorry about that. I just realized that that's the case. Okay. Okay, here we go. So dynamic systems are systems that are defined by differential equations. Static systems are systems that are defined by algebraic equations. Think about individual components. For example, a resistor is a system with a static model. Why? Because there is a simple algebraic relationship between the voltage and current. But a capacitor is a dynamic component because the relationship between the current and voltage is defined by a differential relationship. Okay? Let me give kind of another axis here. Horizontal and vertical are purely arbitrary. We can have a lumped parameter model versus a distributed parameter model. Sorry, it's not very visible. Distributed parameter model. Now the difference here is that in the lumped parameter model, the signals are only a function of time. Okay, remember a lumped parameter model is where you can define components that are interconnected together. And it's all about, for example, component voltages and component currents. We don't care about what's happening in between in circuit theory. A distributed parameter model is where you have variables that are both functions of time and an additional variable. For example, space. For example, you can have here v of t. Here you can have v of t and x. Think about a transmission line. The voltage across a transmission line is a function of time and is also a function of where you measure the voltage across the transmission line. Okay, distributed parameter models will be something that's going to be new and something that we will discuss in this course. But up to now, both in 302 as well as in circuit theory, you often dealt with lumped parameter models. Okay. Now you can have another axis, and along this axis you can have, on one side you have continuous time, and on the other side of this axis you will have discrete time. What's the difference? The difference is that in the continuous time case, the time is a continuous variable. In discrete time, you only care about function or variable values at distinct instants of time that are equally spaced in time. Okay? So in the continuous time version, you are using Laplace transform to actually talk about the frequency domain analysis. In the discrete time, you talk about the Z transform. Okay, so this is like EE402, and this is like EE302. Okay. Yet another axis that we have is that we can have linear systems versus nonlinear systems. Okay? We are very familiar with linear systems. We are not that much familiar with nonlinear systems. We will become familiar with some nonlinear systems in EE407 and EE406. Okay? So what's the property of a linear system? Is the superposition property. Like if you apply one input U1 and you get an output Y1, and you apply another input U2 and you obtain a response Y2, if you input to this system a linear combination of U1 and U2, like A times U1 plus B times U2, the response to this combined input signal will be a similar combination of the output responses. That means A times Y1 plus B times Y2. That's the superposition property. Okay, so in the linear systems, you have superposition that holds, and this is what we have seen mainly in 302. Okay, so another axis here is where we have deterministic systems versus on the other side we have stochastic. Okay, so we have dealt with deterministic systems and we will keep dealing with deterministic systems for now. EE407, EE406. Stochastic systems arise when you have a probabilistic relationship between the input and the output. Okay, we will not be diving into stochastic systems in the undergraduate level, but we have graduate courses that are addressing particularly this part. In part, for example, we have probabilistic robotics course that will be talking about what happens if you introduce non-deterministic phenomena and non-deterministic effects of sensors, actuators, what kind of controls we can have, and so on. Okay. Finally, I have here change-oriented systems versus what is called discrete event-driven. Okay. Now, what's the difference? We have mainly dealt, and we will keep dealing with change-oriented systems. So in 302, 407, 406, change-oriented systems are where variables are a function of time, essentially. Everything is a function of time, be it continuous or discrete. Everything happens regularly with the change in time, okay? In discrete event-driven systems, changes happen in response to some other variable changing, okay? This often arises in, for example, manufacturing processes, okay? For example, a part arrives, and when you detect that a part has arrived, you do something. So changes are initiated by other variables, okay? So that's going to be outside of our scope, but we have actually a graduate course. Discrete event systems is actually the name that actually analyzes stability, all kinds of behavioral issues with discrete event-driven systems, okay? One thing that I haven't included, but I will include here, is actually time invariant and time varying. What's the characteristic of a time varying system? Is that the system parameters themselves become a function of time. In the time invariant case, for example, in the Laplace domain, system parameters are all constants. But in time varying systems, parameters themselves become a function of time. Okay? Now I will give examples on each one of these different, or not all of them, but those that we will be concerned about in this course. I will try to give examples on in the coming minutes, actually. Okay. Now let me finish the course by a small exercise again. If you can just go to your Metu class in your web browsers, there will be a very short 3-minute kind of session exercise. I'm going to make that visible right now, and that's going to finish for today, okay? So hold on, let me see the session exercise, and I'm gonna make it visible, okay? And I'm gonna start sorry, something happened with this. Let's see whether there is okay, so that was kind of a mistake that I made. Okay, here we go. So session exercise, I'm opening up that one. How can I? Okay, so you should be able to take that right now, if I'm not mistaken. Let me see the timing. Let's make this 50. Okay, that's a 3 minutes exercise, and you should be able to take it right now. Okay, so can you start it at this point? Arkadaşlar, egzersiz...
Hocam açılıyor şu an, başlayabilirim.
Bir saniye, başlayabilirsiniz. Yalnız bir eko sorunumuz var. Neden? Çünkü mikrofonum kapalı, başka birisinden eko yapıyor.